Okay. All right. This is actually going to come up today as we are starting to talk about the idea of threads. We kind of ended last class. I did set an alarm this time to see if that'll give me the 2 minute warning. I'm so used to teaching 75-minute classes, so it's I don't know. I just get into whatever I'm talking about. But anyways, we were talking right at the end about the idea of pass by value versus pass by reference, whether something's getting sent in as a copy or something's getting sent in as a pointer to the actual place in memory. And we were looking at how Java handles this from an object perspective, since Java takes away our opportunity to decide, is we don't have that syntax for dealing with memory or not dealing with memory. We don't have that pointer syntax. Java included inside that object, that top level object, the ability for us to ask an object to clone itself, effectively saying, become a copy of yourself. Yes, you still live in a place in memory, but you're a different place in memory than the whatever part of the program called this function was using. So it allows you to kind of get around the couple of situations that might pop up from time to time dealing with not having a syntax for pointers. So I would say in general, it's an upgrade. The idea of not having to deal with pointers, certainly from a um, inexperienced programmer perspective, Java prevents you from accidentally writing very inefficient code by passing gigantic objects by value, something like that. Um, but at the end of the day, we have tons of RAM, so probably not that big of a deal anyway you cut it. All right, so first, what is blocking code? Let's just demonstrate it here real quick. So I'm just going to go ahead and start a new project. And let me just save it real quick. Well, actually, let me flip the language and everything. So we'll switch to Java. Um, you've seen me, I like to name my main class driver. So I'll just stick with that. But remember, once I rename it here, I also need to rename the name of the class. So you could make the argument that just for making a stupid little name change, I just added in some error proneness to my code, but we'll call it good practice. But I like the idea of connecting the part of your program that has main in it to the thing that drives your entire application, which then connects it to that idea of installing drivers for like video cards and things like that. That's the software that drives that piece of hardware. All right, so I kind of like our central thing just being driver. All right, I'll go ahead and test this real quick just to make sure we get a nice hello world down there. So now we know our development environment is working. So now we want to see the problem that threads are going to help us overcome. And we'll talk about threads here in a second. So let's say that I want to write a for loop. Let's do it 100,000 times. We'll just print out I each time through. All right. So this code right here, we could say that code blocks us from getting to this line of code, which means that we do not get to line 17 here until this for loop has completely completed. It has to go through its entire process before we get to continue on through our program. All right, so if we run this, we'll see we get a whole bunch of numbers printed out, and in the end, we'll finally get hello world. And I'm going to show you something else here just in case I haven't shown you before, but I probably have. So you saw we had to wait several minutes there. Well, not several minutes. We had to wait, what, 30 seconds or whatever for the thing to run. Just to give you an idea here, let's just do something called count. And we won't print out in here. Instead, we'll just say count plus plus. And we'll go ahead and run this, and we see we get hello world almost instantly. Okay, so what does that tell us? This is getting in a little bit into operating system stuff. Good. Well, this one line here is all I commented out, right? The thing that prints to the screen. So I'll put that back in, and now we see it takes our 30 seconds again, right? So what we're really seeing here from an operating perspective, operating system perspective, which is related to what we're going to be talking about with threads, is that when we write something out to the screen, it's expensive. Okay, so input output is an expensive thing and actually has to interrupt the CPU doing something called a context switch, which makes your operating system run extremely inefficiently. Because you're typically when you take the OS class, you'll talk about different ways of scheduling the CPU to make you feel like all your applications are getting CPU time all the time. But the reality is behind the scenes, there's some algorithm that's trying to schedule all the tasks, all your open programs or whatever, to get their share of CPU time so you feel that everything is working in real time. Well, we are short-circuiting that every single time we try to do any output to the screen. Not a big deal for a single print statements here and there, but when you throw print statements inside of loops, you saw how much it added up to time. And that was also, call it wear and tear, at least real-time wear and tear on the operating system, having to load stuff onto the CPU, then I'm almost immediately having to unload it from the CPU to let the next guy in, just so this guy can go get in line to do some IO, and then ultimately getting back in line for the CPU, only to be kicked off again the very next iteration through the loop, which is 2 instructions or something like that. All right, but anyway you cut it, we saw that all this stuff has to happen before that hello world occurred. Now, well, this is a stupid example. What if we had things that we actually wanted to, whether it's actually happening at the same time or not, we wanted them to behave as if they were. That is, we wanted to have code that did not block us from doing something else. So an example of this would be like a authentication type thing. So you go to some website and it's asking you to log in with your username and password. Well, that's something that you expect to not block somebody else who goes to that site to put in their username and password. Because you might start typing in your username and your password, then you walk away to get lunch. So now you're holding up the line for an hour, right? That's not that's not our expectation. So there has to be a solution, right? There has to be something that allows kind of this incoming phone call, if you will, for them to then hand it off to somebody to deal with them so that you can listen for the phone to ring again. Okay, that's the problem that threads solve. So blocking code is code that prevents us from moving to the next section of code until it is finished. What if we don't want that? We have to utilize the OS's ability to run multiple processes at one time. All right, so this gets into the difference between something called a process and something called a thread. So a process is, let's call this heavyweight. A thread is lightweight. So if I open up the terminal here, These are all the processes currently running on my computer, full-fledged processes, not threads. So each one of them has a process ID. They have the whatever commands are running here. It shows you the percent of CPU time that particular process is running. This Unix program called Top shows you the things that are taking up the most of your time or whatever, but it's letting us get a view of what's going on here. It shows you the amount of memory it's using and all these things. So processes are big boy data structures. Somebody wrote an object when they were creating this operating system called a process. And inside of that, they have a whole bunch of fields of things they're keeping track of for that process. And some of those fields deal with what I mentioned a minute ago or a couple minutes ago with that idea of context switching, where you have to remember the current state of the CPU. So that gets into the whole other area. We talked about CPUs last semester, where a CPU effectively is, we say, oh, it's a central processing unit. It's the brain of the computer. But what does it really do? It follows individual instructions. And, so it's a whole bunch of magic tricks that the CPU knows how to do. And if we call those magic tricks in the right order, I probably had us do something like this, wiggle our fingers and do all sorts of little stupid stuff that, don't seem to mean anything, but when you put all those together, you can accomplish doing something. CPUs work the same way. Um, so the when a process gets its CPU time, it has to, let's say it gets its CPU time for the first time. It will start running its code, start running its programs. It's going to be storing pieces of information. You'll be starting to work with assembly code in your computer organization class. We saw assembly early on last semester when we looked at the Hello World Linux assembly program. So a lot of times with assembly code, what you're doing is you're taking something and you're loading it into this place in memory on the CPU. Something else, you're loading it into this place in memory on the CPU. So the CPU has all these little cubby holes on it that can hold pieces of information. So while that stuff is stored in the CPU and your process is getting its CPU time, um, everything's going well, but all of a sudden that process gets interrupted, whether it's run out of CPU time naturally or it had to do some IO and it's kicking itself off the CPU. Any way you cut it, when that process context switches, when it leaves the CPU, it has to keep track of all the current state of the CPU, all the values that were stored inside of all the little cubby holes. It has to remember inside of that process. It's called a PCB, process control block, is the object behind a process in an operating system. But it has to store a whole bunch of fields to keep track of the state of that process when it gets back onto the CPU so it can fill up the CPU with new stuff, print its one line, or try to print its one line out, then kick itself off again. That's why it's so inefficient. It's constantly packing and unpacking its bags, remembering the current state of the CPU when it's maybe only issued two, executed two instructions in the middle there. All right. So in any case, processes have a lot going on with them. They're important. At the operating system level, us having individual processes is I guess it's an important feature. But if we're starting to talk about our own program, where we're writing the program and we want our program, which is going to have its own process, and typically processes are implemented in terms of threads. So modern operating systems typically, when they create a process inside of that, they spawn kind of like a master thread that process is running under. Um, But if the programmer themselves wants to start creating the ability to have non-blocking code, we used to have to use create new processes. So we used a Unix command called fork. Um, so uh, and you've probably seen this on it's on GitHub, which then makes it's on our online GDB if you want to, if I send you a copy of code and you want to fork that code. So fork is an old C program that generates a new process. full-fledged big boy process. So typically when you write a program in old style C that forks, you'd have your program running to this point, and then what you'd have, you had a call to fork. And at that point in time, your program is cloned. And fork returns to one of them a zero, letting you know that you're the parent, actually letting you know that you're the child. And the other one gets the process ID of the new child that was just spawned. Okay. So from that point forward, your code is all in one place, whether it's the parent's code that's executing or the child's code, it's actually all in one program. So it's already pretty inefficient from a typing perspective because everything gets all, especially if you're going to be spawning off a whole bunch of processes, you might have different things in there. Go ahead. Your first part is correct. A process is a program in execution. A thread would be a something that runs within a process. So it's has a lot of things in common with the process, but ultimately it answers to its parent process. So you could have a program that has five running threads in it. And we'll see one here in a few minutes. And that program, those threads share the single CPU time with the parent. So if your parent's getting 5 nanoseconds on the CPU and you spawn off five threads, those threads are sharing that 5 nanoseconds. You don't all of a sudden get 25 nanoseconds. But in the olden days, before we had threads and you were using the fork system call, you were actually creating a real deal process, a whole nother thing for the operating system to manage, which then also gave that process its own CPU time. So you could actually write programs that made you could have a program that effectively increased its performance on the computer because it would say, okay, well, I can do 3 or 4 things at once that don't necessarily, interact with each other. Because you certainly it's the chicken or the egg problem, right? You certainly can't do step 2 until step 1 is done in many applications, right? You don't flip the pancake until you've already put the batter in. Those things happen to happen in a specific order. All right. So maybe threads aren't the best solution for that. You want to have blocking code, pour batter, wait. Once you see the little bubble things, then flip pancake. So on and so forth. Yet, if you're making pancakes here and you're making coffee over here, those things don't have anything to do with each other. They're not reliant on each other. So you can technically have those happening at the same time as long as you had enough hands or whatever. Makes some sense? So in the olden days with full-fledged processes, you would make a call to the fork system call, which would then give you a brand new secondary process, which would get all the benefits of a normal full weight process, including extra CPU time. So programmers could then circumvent the efforts put in by operating systems to give the end user a good performance, feeling like their programs are being fairly distributed on the CPU so everything feels like it's running at once. And instead, you could have a program that spawned off 20 processes, ultimately taking over a lot of the CPU time, so the rest of your programs feel sluggish. Go ahead. Chances are that'll probably be threads, but it's possible modernly that you might have a video game that maybe spawns off maybe 3 or 4 top level processes because they're each kind of almost, you can think of a big application like a video game, maybe kind of being like 4 individual applications that kind of are running on their own that might need their own CPU time. But then each one of those might have a bunch of threads within it. And we're going to see how threads work. We're just talking about the background behind the threads. We're not going to work with processes. We're going to create some threads. And you'll see that spawning them is like 2 lines of code. It's not a major issue, but not every problem benefits from either multi-processing or multi-threading. Um, so this idea of the fork system call also became a major security problem with a lot of operating systems. That is, you've probably heard of a denial of service attack or a distributed denial of service attack. The early versions of those basically had somebody just hitting a computer over and over again, spawning off processes. Well, just like we talked about earlier in the week, um, our modern operating systems, maybe it uses a 32-bit number for its process IDs, right? Which gives you, 4 billion unique process IDs. Well, if you have a distributed attack where you have a zillion computers all hitting this one computer, each one spawning off a process or spawning off as many processes as it can, you pretty quickly will run out of your 4 billion process IDs. And now no more applications can be open on that computer because it no longer has a unique process ID to hand out, including the application that the system administrator was going to try to open to kill off processes. So they can't even get to the computer. The only way to fix it is to reboot the machine. So that's why denial of service is kind of a headache, but an easy problem to fix. But sometimes rebooting is a big problem when you have like live backups running and stuff like that. So lots and lots and lots of problems giving programmers direct access to the process structure in an operating system becomes dangerous. We've put a lot of layers in there where it's less dangerous today than it could have been. There's a limit to the number of processes an individual program can run that's running in user space on an operating system. But bottom line is, let's call it 99% of the time, you're going to use threads, not processes. You'd have to have a really good reason for wanting to have multiple processes where maybe your big application really should exist in 4 separate applications. Then I can see how a large video game might make that decision. Good news is we also have CPUs that have multiple cores in it, right? So if you have a quad core CPU, so it can technically do 4 things at once, and you have 4 separate processes, those 4 processes can all have actual CPU time at the same time, as long as they're not reliant on each other. So it's a big game, but understand that your operating system is kind of one of the players in the game. So as a programmer, when you're writing stuff, you have to consider the impact this is going to have for large applications on the larger ecosystem of your operating system. Is your program one program that's only running on this operating system and that's the only thing that ever runs on this operating system? Maybe it's a computer that's operating as a web server where effectively it runs Apache. Then it doesn't matter if Apache is getting 100% of the CPU time. Everything else is running as a thread underneath that. Okay, so that's what a fork is. Old C program that generates a new process. Inefficient. Only use when needed. And then I'll say you will know when you need it. When you get to the point that it's an actual decision you have to make about this, you will be an experienced enough programmer to know the difference. So just kind of throw that in the back pocket. But that's where that word comes from. When you make a copy of the current program, you fork the repository. Always when you're talking about the fork system call, make sure you fully enunciate. Can turn into some pretty awkward conversations sometimes, especially when you start talking about child processes and things like that. There was an incident 20 years ago in a diner that, yeah. So in any case, let's talk about threads. Threads. This is a lightweight process fully owned by the parent process. So it is something less than a process. Doesn't have to keep track of as many fields, attributes. So that we talked a minute ago about that process control block, the object associated with a process in an operating system. To implement threads, that thread control block is a much smaller thing. You have less stuff to keep track of. You don't have to keep track of the state of the CPU and things like that, because you already have a parent that has one of those data structures. You're a much smaller thing within it. All right. Now, just quickly talk about this. We mentioned this last semester. Within object-oriented programming, like in Java, we have this thing called an interface. And an interface kind of looks like a class, but this is a structure that defines specific methods slash fields that I'm going to say implementing objects must define. So to show you the real example of this, there is an interface called runnable that lives in Java. Java runnable interface. So what this guy says is you must have a public void run method. So you'll see this guy is not, so its type is of interface. So think of this as basically an unimplemented class, just a set of rules you have to follow. Kind of like saying something is USB compatible. We would say something is runnable compatible. It's implemented all the pieces that are expected of something that's runnable. So in this, that means you have to write a function called void run to meet the requirements of the runnable thing. All right. So when would you use something like an interface? I think that whole USB compatible thing is a decent real world example, where if you are a company, you're one of 1,000 companies that make USB things, right? That plug into USB ports. It is on you to make sure that your physical thing you're plugging into a USB port internally implements all the features of the USB protocol. Right. So the IEEE standard for USB says, here's all the stuff that USB 3.1 must do. So if you're making a USB device, you're responsible to be USB compatible, which means you have to make sure it supports all that stuff. Same thing here. If you're creating something that you want to be a runnable device, runnable program, it must meet all the standards of things that are runnable. All right. Which in this case is a very low bar. It just has to have a single function called run. That's the job of interfaces. Now, you might go through your whole career and rarely ever use an interface directly. So why are we learning about it? It's not that it's unimportant, but generally interfaces fall into the category of kind of self-policing code, where if you have things that all need to be compatible with each other, you might create an interface that says everything has to have this, so that when you go and create objects that you intend to implement that interface, instead of using the keyword extends, you use the keyword implements, which basically says, I intend to be compatible with that interface. So then when you create an object that's missing something, it screams at you, instead of you having to run into a bug at some later point in time. Most programmers probably don't highly leverage interfaces on any sort of regular basis. You'd have to start getting into a larger kind of a multi-developer thing, maybe writing a video game or something like that, where you have 50 developers working on something and they're all working on separate parts of it that need to be compatible with each other. There might be an overarching interface that they run with. But for us, working with threads, we're just going to use a class that's built into Java already called thread, which already implements runnable. So we have this class called thread. Its only parent is object. So this is a very low level class. It implements an interface called runnable, which tells us a thread has a method called run that takes no parameters and returns nothing. We don't necessarily know much about what it does. We just know it has that. Okay. So that's what a thread is. We're going to come back to this, call it shortly. But what I'm going to do first is let's go in here And I'm going to say thread T1 is equal to a new thread. Thread T2 is equal to a new thread. T1 dot start, T2 dot start. Right? I'm going to run this program and we're going to see nothing happens. But I did spawn off 2 threads that did nothing. The thread class in and of itself does nothing that we will see. Because that run method inside the thread automatically gets called when we tell a thread to start. But it gets called in the super secret way that threads are required. Threads built into Java are directly communicating with the operating system in a way that a Java programmer cannot. So we are reliant on the thread class to do the magic of spawning off threads. So there is some magic that's happening here in that start function that is not something available to the Java programmer. It's something that was built into the language to work directly with the operating system for creating threads. But what I'm telling you is when you call the start function here for a thread, anything that is a thread, so we're going to create classes that extend thread. So when you call the start method for a thread, what it immediately does is it does its magic thing that we don't have any control about, but finally it calls the run method. And the default run method in the thread class has nothing in it, as we just saw. So I promise a real thread was created. The operating system spawned off a thread. It spawned off another thread. It told both threads to go ahead and start. Then the parent thread died, which made this, which made the 2 child threads die, and there was no output of our program because it was running a run method that had nothing in it. So we might want to create a run method that does have stuff in it. So I'm going to go ahead and create a class. I'm going to call this guy a worker bee. So we can think of our threads as kind of like little worker bees in our program. Okay, so it's going to be workerbee.java. All right, so this will be public class worker bee. And we're going to say this guy extends thread. So right from the get-go, this guy is a thread, right? So if I do nothing else here, and I just replace all my calls to thread with worker bee, I created a new object that is a thread. It's just called worker bee. I've done nothing to differentiate itself. As a reminder, that's what inheritance is about, right? Inheritance allows us to start with a baseline and then differentiate ourselves from that baseline. And in our case, our differentiating feature here might be that, oh, I want my run method to do stuff. Make some sense? So back here in worker bee, we can say public void run. So what this guy is doing, this is overriding the default run method we inherited from thread. We're making our own. Remember how variables resolve, methods resolve the same thing. A variable or a method resolves to its most local definition. So when our worker bee has its run method called by its start method, it will find worker bee's version of run before it finds thread's version of run. It'll bump into our more local definition of run that we're writing right here. So inside here, I'll say for int I is equal to 0, I is less than, let's just do 100,000 again, I plus plus. Print out I. So now that's what run does. And maybe at the very end, we just say system.out.println. I'll print out this, which should give us, what will the this keyword print out here? Nothing I taught you today. It's something that's true of every object in object-oriented programming. What do you think? What's going to display when I try to print out this? What is this? What is the this keyword? Go ahead. Yeah, so it's how an object refers to itself from within itself. So this, in this case, is this instance of worker B, right? So it's probably going to give us a memory addressy thing uh, with worker B on it, like worker B at some hex value. Unless, what could we do to worker B to make it so that it prints out something other than that memory addressy thing? Override toString that we got from object, right? So we'll go ahead and run this. So now I have my worker B. Oh, I got to name my project thread practice, whatever. All right, so I'm still creating my worker bees, telling them to start. I haven't even written a constructor, so I'm just utilizing the default constructor that doesn't do anything special. All right, but now my more local run method does some stuff. I do some counting, I do some printing, and in the end, I print out I'm whatever this prints out, which will be the memory address. So in the end, we'll see two separate worker bees with two separate whatever, two separate things printing out. Now, at the same time here, I'll go ahead and take that same code and I'm going to put it after the parent. That's weirdly indented, but whatever. All right, so now create two worker bees, tell each of them to start. So those two worker bees are going to be off counting, printing, blah, blah, blah. But these do not block. So these will spawn off. So this does not block. Does not block. So while those worker bees are off to the races doing their thing scheduled by the operating system, we don't have to do anything about them. They're just off to the races running whatever their run method says. We get to this code right here, and the original driver is still cooking, still running its thread. So there's 3 threads in existence here. We have a top level process, which has an owner thread, a top level thread. So that's the thread running for driver. And then we spawned off 2 child threads and told them to go do something in the over here while I go and do something else here. In fact, actually, maybe we want to not have this guy count. We'll have too many numbers just being counted. So let me just have driver display himself. So we'll see that that hits right away while all the other children are still cooking. Oh, yeah. This is not going to work here because this is a static um, uh, function. Main is static, so we don't have access to this keyword. So we'll just say parent done, something like that. So there's the children kind of off to the races. Maybe going to be a little hard to see the difference here. Let me just have them do this so we can see the. Let's do that. So there. Parent finished. Here's one of our threads. This is what actually, so it looks like thread did overwrite their toString method to make it look like that. So this is thread 1. This is thread 0. So those are our 2 threads. That's the output of the run method for those threads. And the parent finished as well. You can't always rely on the order you see things in here for when they actually finish, because this is IO as well. And we said IO is slow. So you're at the mercy of how the operating system scheduled this stuff. This is something called a race condition, which effectively says if you're reliant on the timing of your threads, you're doing it wrong. If you specifically need to wait for threads to finish, there's a way to accomplish that. There's a way for us to wait for threads. So if we go and look at the thread class here, we can ask the thread class. For instance, there's a static keyword here, and it'll tell us the number of threads that are active. And since this guy is static, that means we call it with the name of the class, right? So I could go here and out in driver, I can do a system.out.println red dot, what's that called? Count. Active count. What I'll do just for timing purposes, as soon as I spawn off that those two threads, I'll go ahead and have the parent report the number of active threads that there are out there. See, we have 3 active threads, the parent's thread, and the 2 threads he just created. So we can learn about all these things with threads. We get our own clone method, all this stuff. But when we get down here, you can get names for your threads and stuff like that. We get down here, we have something called join, which tells us to wait for a certain thread to finish before we do anything else. So there's also a version of join that says, the longest I'm willing to wait is this number of milliseconds. So if we want to do that to guarantee an order, I can go here and say T1.wait, T2.wait. So these 2 lines block. So the parent creates 2 worker bees, tells both worker bees to start, outputs that there's now 3 threads in existence. And then the parent says, okay, I'm going to wait for my children to finish their tasks. So he'll sit right there. And then in the very end, once thread 1, thread 2 are done, then our parent will finally display. Now, right now, our worker bees are not doing much, so this is going to run pretty quickly. I'll come to that in a second. Go ahead. Oh, this is going to take 2 seconds just to get the error to go away. Bad programming practice, but that works for. So if I go back to where the error that we just had was, it says, my 2-minute warning. It says unreported exception. We have an interrupt exception. It says you must catch this in order to use the wait function. The proper way of doing that is with a try catch. So you would say, I want to try to do these 2 things. Catch anything bad that might happen, and then say, deal with it yourself. Like that. This would be the correct way of dealing with exception handling. And we'll talk about exceptions in more detail. When I just say throws exception up here, I'm basically avoiding having to type all this and just passing it up to the Java virtual machine and saying, hey, it's your problem now. But that's the way it wanted me to try to do those things. So notice here that it did get an exception. I actually wonder what that e.print stack trace. Well, I'll have to look at he's an exception, but whatever. It's getting some exception, so you're seeing what the catch is. So it tries to do these 2 things. It did end, but there's probably some timeout or something on the thread. But in the end, we saw that our parent was the final one who finished. It waited for both strings to die. All right, so question, there will be homework over the weekend dealing with the stuff we just talked about. I'll put it up on Blackboard. So what was your question? Okay, which one? Which aspect of it?
the output was before you made modifications to it.
I got you. Yeah, gotcha. So before, I think actually parent done, actually it came up first, right? Yeah, so, but there was no guarantee of order there. So because of that whole thing I talked about where you're at the mercy of how your operating system is scheduling for the CPU, they're all fighting for CPU time. They're all fighting to be able to write something out to the screen. So you're at the mercy of that. When we do a wait like this, we're basically saying, I'm going to wait for you to finish. I'm going to wait for you to finish. All right. So you're going to be building in the wait thing to the homework assignment. I'll give you a little sample code as a starting point, but the assignment is effectively a ping pong thing where two threads count with each other. So 1, 2, 3, 4, 5, simulating some communication between them. Questions, comments, concerns, bribes. All right, I'll see everybody on Monday.